Good day. My name is Dr. Adetunji. So this is the lecture on function of complex variable. So what we first need to look at is what are complex variables? They are variables that can take on values of complex number. For example, z, which can take on a and b as a complex number in the form of z is equals to a plus ib. So z here is reversed as complex variable while a and b are real number. So So also, what is complex number? A complex number is a number of the form that can be expressed in the form of a plus bi. Like I said earlier on, a and b in this expression are real numbers, while I is an intermediate satisfying I squared is equals to -1. So therefore, we can say that a is the real number or the real part of the complex number, and b is the imaginary part of the complex number, so denoted by imz and rez. So this implies that there are two parts in the equation of the form z equals where re is the real part and iz is the imaginary part. But this complex number has properties. One, one of the properties is what is known as equality. That is, when a, b are real numbers and we have a plus ib is equals to 0, then automatically a should be equals to 0 and b should be equals to 0 based on the properties of equality. So also when a, b, c and d are real numbers and we have a plus ib which is equals to c plus id, then we can also say that a is equals to c and b is equals to d. So another three, for any three, for any three, the set complex numbers Z1, Z2, and Z3 satisfy what we know as commutative law, associative law, and distributive law. So we shall see how these operate in the next slide. So also another properties is the sum of two conjugate complex number is real. That is, when you have two conjugate complex numbers, their sum is always real. Likewise, the product. So if you look at the diagram, you will see that we have a kind of a Cartesian diagram, but in this case, I've combined both the normal Cartesian coordinate and also the real, the complex number diagram together. So if you look at the picture here, we are seeing that from the origin 0 along the x direction, which we know very well, so which is also equivalent to the real axis, which is denoted here as RV. So along the y-axis, which is here represented as B, which is the imaginary. Then, if you try to look at the diagonal now, from origin with this arrow, so we have what we know as Z, which is equal to A plus IB. So this clearly describes how a complex number operates in a form of a Cartesian coordinate. So now, like I said earlier on, the commutative law, that is, when you have two set of complex number, let's say Z1 and Z2, if you add them, they should be able to give you Z2 plus Z1. So in this case, you said they are commutative law for what? Addition. If you multiply them also, they are known as what? Commutative law for multiplication. The same thing when you have Z1 plus Z2 about three complex number. So they should be distributive. For example, the first one here, this implies that this law is associative for addition. That is, when you had Z1 plus Z2 and then plus Z3, you should be able to have Z1 plus Z2 plus Z3. That is, when you have these two together and you add it to this, it should give you this. The same thing for multiplication also. We have associative law for multiplication. Likewise for additive. So now let's look at some examples now. I said examples, given that Z1 is equals to 2 minus 4i and Z2 is equal to 4 plus 6i and Z3 is equal to 5 minus 2i. Show that Z1 plus Z2 is equal to Z2 plus Z1. 2. Z1 dot Z2 is equal to Z2 plus Z1. Like that, up to this point. So the second question is, given that Z is equal to Z, where AB, AB are real numbers, show that the product of the two conjugate complex number is real. The last one is show that the absolute of Z1 plus Z2 is less than or equals to Z1 plus is less than or equals to the absolute of Z1 plus absolute of Z2 if Z1 is equals to 3 minus 4i, and z2 is equals to 5 plus 2i. So now let's see how we can solve this problem. Now, if you look at it, this is the solution. The first one, we have z1 to equals to 2 plus 4i, and z2 to equals to 4 plus 6i, and z3 to equals to 5 minus 2i. If you add them, z1 plus z2, this is a log, is equal to z2 plus z1. So z1, which is 2 minus 4i, and z2, which is 4 plus 6i. So if you add the x in this case, which is 2 plus 4, that gives you 6, and minus 4i plus 6i, that gives you plus 2i. So in this case now, if you consider z2 again, you have 4 plus 6i. When you add them, you see that the same result you have for z1 plus z2 is what you have for z2 plus z1. So therefore, we have proved that z1 plus z2 is same thing as z2 plus zi. Let's look at the multiplication aspect of it. So z1 times z2. So 2 times 2 minus 4i times 4 plus 6i. You multiply 2 times 4, it will give you 8, minus 4i times plus 6i. That gives you 24i squared. And we know that I squared is equal to minus 1. So if you put it here, you now have 8 minus 24 times d, that will give you 8 plus 24, which is 32. We do the same thing, z2 plus d, we also have what? 32, which shows that z1 dot z2 is equal to z2 dot z1. This is uh, the multiplication law of additive, multiplication law of associative. So the same thing, the third question there, if you try to expand this like I did here, you see that the right answer is 11 and the left answer is equal to 11. So we prove also that this thing is what? Distributive in nature. So if you have these two now, z1 plus the conjugate of z1, if you see something like a bar on top of this, it means conjugate. So conjugate means that, for example, look at this, z1 is equal to 2 minus 4i. Then when you look at the conjugate of z1 now, so conjugate means that you change the sign between the real and the imaginary. The sign here is minus. By the time you take the conjugate, it become positive. So if we add the two together now, it gives us this, which is 4. That satisfies that when you have two conjugate number, when you have two complex number, and the conjugate of this is always produce a real number. Any question? So now, we now goes to the next thing, which has to do with limit. So the limit, most of us are familiar with the concept of differentiation, but before you go deep into differentiation, you need to understand some basic assumptions. So there are rules that we use in limit in differentiation. Rule 1 now, if you have limit of c, which is a constant now, it's equal to c. So if x is not tending to a, so as long as you don't have x in this function now, so automatically the answer is the same thing as the constant. So take for example, find the limit of 4 when s tends to 2. Since 4 is a constant, that is a constant, doesn't have any variables behind it, then therefore the limit of 4 as s approaches 2 is what? 4. Look at the second rules now. That is when the limit of s is equals to a. So now, as s tends to a, what happen? Take for example now, we have find the limit of x when x tends to 10. So where you see x, you pick the value of what? X as the limit. Then if you put x is equals to 10 into the limit, then you now have as x tends to 10, the limit is equal to what? 10. So look at the third rule now. The limit of cx is equal to, we can write this as, since this is a constant, you can bring it out and allow the limit to work on the variable of x, that is as x tends to a. Take for example now, an example is find the limit of 6x. So in this case, 6 here is a constant. If you bring it out, you have 6, then the limit of x. Now, x is now going to 2. You replace x with 2. That will give you 6 times what? 2, which is what? 12. Now, another good rule is when you have the limit of f of x plus g of x as x tends to a, this we can split it since you have addition in between it into two different functions. The limit of f of x as x tends to a plus the limit of g of x as x tends to a. Look at a very good example. Find the limit of 5x squared plus 3x as x tends to 2. So in this case now, if you apply this rule on this now, we now have limit of 5x squared plus 3x. So since 5 here is a constant, you can bring it out, then now have limit of x squared as x tends to 2. The same thing, 3. limit of x as x tends to 2. So where you see, just put x and perform the operation, you now have that this is x squared, this is 2 squared, and this is x, this is 2. So 2 squared times 5 will give you 20, 3 times 2 will give you 26. Another good rule for limit is the limit of f of x times g of x. In this case, you can split it like we split it for addition up here. So you have this. An example is when you have limit of 3x squared dot 8x. So as x tends to 2. So in this case now, we can split to limit of 3x squared times limit of 8x. The two functions are subject to approaching 2 when s is going to 2. So you do the same thing, then you have it to be this. Another one is limiting of f of s over g of x, which is equals to the limiting of f of s tends to a, divided by limit of g of s as s tends to a. Good example is find the limit of 3s over 6 as s tends to 2. So in this case now, we can write it as the limit of 3s as s tends to divided by the limit of 6 as s tends to 2. So since below is a constant, automatically we know it will just be the value of that constant, which is 6. Then the up, you have only one variable, x. Is not an exponential one. It just be 3 times 2. It should not be 3 times 2 divided by 7. That give you 1. Another good one is this. The limit of this, of the square root of f of s of n, which is equals to this. So let's, I think we'll be able to go through some of the concepts. Then this is an example, an assignment for you. You have to find this, find the limit of the following functions. I've solved some of this example. It is only this one that I have not tried to attempt, but it's a very simple thing. You can only use the last rule here, the last two rules here to solve that problem. So I want you to solve this problem before the next class, and in the next class, we look at it together, or during our discussion, we look at it together. Thank you very much for coming for class, and see you next week. Thank you. Bye-bye.